Long before telescopes, before equations, before the quiet hum of machines listening to distant stars, there was the night sky. It stretched above early humanity, without explanation or warning, vast and dark, scattered with points of light that did not flicker like fire and did not fall like rain. They rose each evening with patient reliability, yet never offered answers. For tens of thousands of years, the universe announced itself only through silence, scale, and repetition. To stand beneath the night sky is to experience one of the oldest human sensations, the feeling of being small in the presence of something immeasurably large. Long before the concept of space existed as a scientific idea, people sensed that whatever lay overhead was not simply decoration. It moved with patterns, it returned on cycles. It governed the rhythms of light and darkness, warmth and cold, growth and decay. Early humans did not separate astronomy from survival. The rising and setting of stars marked time. The motion of the sun shaped migration. The phases of the moon regulated tides, hunting, planting, and rest. In this way, the universe was not distant. It was intimate. It pressed itself into daily life, quietly shaping behavior long before it was named. Across continents and cultures, people looked upward and asked the same questions without speaking to one another. What are these lights? Why do they move? Why do some wander while others remain fixed? Why does the sky change yet never collapse? Without instruments, early observers relied on memory and patience. Generations passed down the knowledge that certain stars rose in certain seasons, that the sun's path shifted over the year, that shadows grew longer and shorter in predictable ways. This slow accumulation of observation formed the earliest foundations of cosmology, not as theory, but as lived experience. Ancient sky watchers did not yet distinguish between physical explanation and meaning. The universe was not merely something that existed, it was something that acted. Storms, eclipses, comets, and meteor showers were not random occurrences, but events demanding interpretation. In the absence of measurement, story filled the gap. The stars became ancestors, animals, gods, and heroes. Constellations emerged not because they were physically connected, but because the human mind seeks patterns even in randomness. The same scattered lights became different stories depending on who observed them. A hunter's bow, a great serpent, a celestial river. Each interpretation reflected the values and fears of the culture beneath it. Yet, even as mythology flourished, careful observation quietly continued. Some ancient civilizations tracked the sky with remarkable precision. Stone structures aligned with solstices. Calendars synchronized with lunar cycles. Long before modern science, humanity demonstrated that the universe could be measured, even if it could not yet be explained. What made the sky especially mysterious was its apparent permanence. Mountains eroded. Rivers changed course. Forests burned and returned. But the stars appeared eternal. The same constellations watched over countless generations, unchanged by human affairs. This constancy suggested that the heavens followed different rules from the earth. That idea, that the universe operates according to laws distinct from everyday experience, is one of the earliest seeds of scientific thinking. Even without equations, early observers sensed that the cosmos obeyed order beyond human influence. As tools improved, so did understanding. Simple sighting devices allowed more precise tracking of planetary motion. The wandering stars, now known as planets, revealed paths that could be predicted. Retrograde motion, once baffling, slowly became comprehensible through geometric reasoning. Still, mysteries deepened rather than vanished. Why did the sky appear to rotate around a single point each night? Why did planets follow loops rather than straight paths? Why did eclipses occur with such unsettling precision? Each answer uncovered new questions, pushing curiosity forward rather than closing it. The transition from myth to measurement did not happen suddenly. For centuries, symbolic explanations and empirical observation coexisted. The universe was both sacred narrative and physical system. This duality allowed astronomy to evolve gradually, preserving wonder even as understanding increased. One of the most profound realizations came with the recognition that Earth was not the center of everything. When careful measurements revealed that the apparent motion of the sky could be explained more simply if Earth itself moved, humanity faced a psychological shift as much as a scientific one. The universe was no longer arranged around human presence. Humanity was embedded within something vastly larger. This realization did not shrink the universe. It expanded it. Suddenly, the night sky was not a dome overhead, but an open depth extending in all directions. The stars were no longer fixed points on a celestial surface, but distant suns scattered through space. The universe transformed from a backdrop into a volume. With this shift came a new kind of mystery. Distance itself became difficult to comprehend. If stars were suns, how far away were they? If their light traveled to reach us, how long had it been traveling? The idea that looking outward meant looking backward in time slowly emerged, unsettling and awe-inducing. The universe, once eternal and unchanging, became dynamic. Stars were born and died. Motion occurred not only across the sky, but through vast expanses of space. Time entered cosmology not just as a human measurement, but as a cosmic dimension. Yet even as understanding increased, the fundamental emotional experience of the night sky remained unchanged. To lie beneath it still evokes the same quiet tension between curiosity and humility. The same questions persist even when their language evolves. What is all of this made of? Where did it come from? Why does it exist at all? Modern observers often forget that mystery is not a failure of knowledge, but its starting point. The universe does not become less mysterious as it becomes better understood. In many ways, the opposite is true. Each layer of explanation reveals deeper unknowns beneath. The earliest skywatchers sensed this intuitively. They did not expect final answers. They lived within cycles, patterns, and questions that renewed themselves endlessly. The universe was not a puzzle to be solved, but a presence to be acknowledged. Even now, with satellites orbiting Earth and telescopes peering billions of light years away, the night sky retains its power. Light pollution dims its brilliance for many, yet the feeling persists. A single clear night away from artificial glow is enough to reconnect modern minds with ancient wonder. When the stars reappear in full, scale returns instantly. Cities feel temporary. Human concerns feel brief. The universe reminds us that it existed long before us and will continue long after. This realization does not diminish human significance. It reframes it. To ask questions about the universe is itself extraordinary. The cosmos has produced within one small region beings capable of contemplating its own existence. That fact alone is one of the universe's deepest mysteries. As we move forward, deeper into space and deeper into theory, we carry with us the same fundamental impulse that guided early observers. We look upward not because we expect comfort, but because something in us recognizes that understanding the universe is inseparable from understanding ourselves. The night sky was humanity's first textbook. It offered no explanations, only patterns and silence. From that silence emerged curiosity. From curiosity emerged science. And from science emerged new mysteries, layered and unresolved. In the sections ahead, we will move beyond the visible stars and into the hidden structure of the cosmos. We will explore what the universe is made of, how it behaves on the largest scales, and why so much of it remains invisible, even to our most advanced instruments. But everything begins here, with darkness, with distant light, and with questions that have never stopped being asked. Once humanity realized that the stars were not fixed points on a nearby ceiling, but distant objects scattered through space, a new and unsettling question emerged. How far away is far? At first, distance in the universe was imagined using familiar terms: journeys, days, lifetimes. But the universe quickly resisted these comparisons. The gap between Earth and the Moon already exceeded anything humans could traverse without modern technology. Beyond that, the distances grew not just large, but conceptually hostile to intuition. The nearest star beyond the Sun lies so far away that even light, the fastest signal known to exist, requires more than 4 years to cross the gap. This realization alone forces the mind to stretch beyond everyday experience. Light does not hesitate. It does not slow. And yet the universe is so vast that even light takes years, centuries, or millions of years to travel between objects. To cope with this, astronomy adopted new units. The light year is not a measure of time, but of distance. It represents how far light travels in 1 year, moving at nearly 300,000 kilometers every second. Even this immense unit quickly became insufficient. Galaxies are separated by millions of light years. Clusters of galaxies span tens of millions. Superclusters extend across hundreds of millions. Each increase in scale distances us further from any physical analogy grounded in human experience. This is the vastness problem. The universe does not merely contain large distances. It exists on scales that actively defy comprehension. When astronomers peer into space, they are not seeing objects as they exist now. They are seeing them as they were when their light began its journey. Looking farther means looking deeper into the past. A galaxy observed at a distance of 1 billion light years appears as it existed 1 billion years ago, long before modern Earth took shape. This creates a layered universe where different eras coexist visually. Nearby stars reveal recent history. Distant galaxies reveal ancient states of cosmic evolution. The sky becomes a time machine, not through speculation, but through physics. The observable universe is defined by this limit. It includes everything whose light has had time to reach us since the universe became transparent to radiation. Beyond that boundary may exist more universe, possibly infinitely more, but it remains inaccessible to observation. This distinction is subtle but important. The observable universe is not the entire universe. It is simply the portion we can see. The true extent of the cosmos may be vastly larger or structured in ways we cannot yet detect. This realization introduces a quiet humility into modern cosmology. Science does not claim to describe everything. It describes what can be observed, measured, and tested. Beyond that lies uncertainty, not as ignorance, but as an honest boundary. Even within the observable universe, scale quickly becomes overwhelming. Our galaxy contains hundreds of billions of stars. It is one of hundreds of billions of galaxies. Each of those galaxies contains its own systems, histories, and structures. To imagine this, astronomers sometimes use simulations that compress scale into manageable visuals. But even these representations struggle. They rely on abstraction because no human mind can truly picture such magnitude all at once. This difficulty is not a failure of intelligence. It is a consequence of evolution. Human perception evolved to navigate environments measured in meters and kilometers, not light years and cosmic voids. The universe operates far outside the range for which intuition was designed. Time, like distance, expands beyond familiarity. The universe is estimated to be approximately 13.8 billion years old. This number is precise in digits, yet vague in meaning. It exceeds the span of recorded human history by orders of magnitude. Entire civilizations rise and fall in intervals too brief to register against cosmic time. Stars live for millions or billions of years. Galaxies evolve slowly, their changes visible only through comparison across vast spans of time. The universe moves not at human pace, but at cosmic pace, where patience is measured in eons. This mismatch between human time and cosmic time creates a strange psychological effect. Events that feel permanent on Earth are fleeting in the universe. Events that feel impossible to wait for are already underway on cosmic scales. When we say a star is forming, we describe a process that may take millions of years. When we say a galaxy is colliding with another, we describe an interaction that unfolds over hundreds of millions of years. The universe is dynamic, but its motion is slow beyond ordinary perception. Yet there are moments of sudden change. Supernovae explode violently. Gamma-ray bursts release immense energy in seconds. Black holes merge in catastrophic events that ripple space-time itself. These moments remind us that the universe is not uniformly calm. It contains extremes beyond imagination. Still, even these violent events occur within a framework of immense distance. Many such explosions happen so far away that their energy arrives at Earth as nothing more than a faint signal, barely distinguishable from background noise. The vastness of space acts as a buffer. It dilutes violence. It spreads energy thinly across unimaginable distances. What would be annihilating nearby becomes whisper-soft across the universe. This buffering effect is one reason Earth remains stable. The universe is not hostile by intent, but indifferent by scale. Catastrophes occur constantly, yet rarely intersect with any given point. Understanding this indifference can be unsettling, but it also offers perspective. The universe is not arranged around us, but neither is it opposed to us. It simply exists. The vastness problem also affects how we understand motion. When objects move at significant fractions of the speed of light, time itself behaves differently. Clocks tick at different rates depending on velocity and gravity. These effects are measurable and real, yet invisible in daily life. This means that time is not universal in the way humans once assumed. There is no single cosmic clock ticking uniformly everywhere. Each region of the universe experiences time slightly differently depending on conditions. On human scales, these differences are negligible. On cosmic scales, they accumulate. Over billions of years, even small variations matter. This challenges the intuitive idea of a shared present moment. When we look at distant galaxies, their present is not our present. We observe them frozen in an earlier state. Their now is inaccessible. Their future may already have unfolded beyond what we can see. The universe, then, is not a synchronized whole. It is a mosaic of moments stitched together by the finite speed of light. Every observation is a glimpse into a different era. This realization transforms the act of looking into space into something deeply contemplative. The night sky is not merely distant. It is layered with time, history, and transformation. When ancient observers mapped the stars, they unknowingly recorded snapshots of the past. Some of the stars visible to the naked eye have already ended their lives. Their light continues to arrive even though the source no longer exists. In this way, the universe contains ghosts, not in a mystical sense, but in a physical one. Light carries information forward through time, preserving images of things long gone. This persistence of information raises questions that extend beyond astronomy. What does it mean for something to exist if its effects continue after its end? How does presence differ from reality when observation lags behind events? These are not merely philosophical questions. They are practical challenges in astrophysics. Interpreting observations requires careful accounting for time delays, distortions, and cosmic expansion. The expansion of the universe itself adds another layer to the vastness problem. Space is not static, it stretches. Galaxies move away from one another not because they are traveling through space, but because space itself is expanding between them. This expansion means that very distant galaxies recede faster than closer ones. At extreme distances, this recession exceeds the speed of light, not by violating physics, but by altering the fabric through which light travels. As a result, some regions of the universe are permanently unreachable. Their light will never arrive no matter how long we wait. They slip beyond the observable horizon as space expands faster than signals can cross it. This introduces a quiet finality into cosmology. There are parts of the universe we will never see, not because of technological limits, but because of the structure of reality itself. Yet, within this limitation lies clarity. Science does not promise omniscience. It offers understanding where possible and acknowledges boundaries where they exist. The vastness problem is not something to be solved, but something to be accepted. The universe is large beyond comprehension. Time stretches beyond intuition. Distance dilutes meaning until only mathematics remains reliable. And still, humanity persists in trying to understand. We build instruments capable of detecting faint echoes from the early universe. We refine models that trace cosmic history back to its earliest measurable moments. We simulate vast structures on computers, compressing billions of years into patterns we can study. All of this effort arises from the same impulse that drove early humans to watch the sky. A desire to situate ourselves within something larger, even if that something resists comprehension. In the next part, we will move from what can be seen to what cannot. We will explore the invisible substance that shapes galaxies, bends light, and outweighs everything we can directly observe. This unseen presence does not glow. It does not emit light. And yet, it dominates the universe. This is where the mystery deepens. When astronomers first began measuring the motion of stars within galaxies, they expected the universe to behave in a familiar way. Objects closer to the center of a rotating system should move faster, while those farther out should slow down. This is how planets orbit the sun. This is how matter behaves under gravity, as it is understood from everyday experience. But galaxies refused to follow this pattern. As telescopes improved and measurements became more precise, a troubling inconsistency emerged. Stars at the outer edges of galaxies were moving far faster than gravity alone could explain. According to visible matter, these stars should have been flung outward into space. Instead, they remained bound, circling their galaxies with unwavering stability. At first, astronomers assumed they were missing something simple. Perhaps stars were dimmer than expected. Perhaps gas clouds were being overlooked. Perhaps measurement errors were distorting results. But the discrepancy persisted. No matter how carefully visible matter was accounted for, there was never enough mass to explain the observed motion. Galaxies behave as if they were embedded in enormous halos of unseen material, exerting gravitational influence without emitting light. This unseen influence became known as dark matter. The term is deceptively simple. Dark matter is not dark in the sense of color or shadow. It does not absorb light or block it. It simply does not interact with light at all. It neither emits nor reflects electromagnetic radiation, making it invisible to telescopes of every kind. Yet its presence is unmistakable. Dark matter reveals itself only through gravity. Wherever it exists, it bends space-time, alters motion, and shapes large-scale structures. Its fingerprints are found not in images, but in equations and observations of how the universe behaves. One of the most compelling pieces of evidence for dark matter comes from gravitational lensing. When light from distant galaxies passes near massive objects, it bends, producing distortions, arcs, and multiple images. These effects allow astronomers to map mass indirectly. In many cases, the amount of gravitational bending observed far exceeds what visible matter alone could produce. The invisible mass required to explain these distortions aligns precisely with the presence of dark matter. Galaxy clusters provide another striking example. These vast collections of galaxies behave as though held together by enormous amounts of unseen mass. Without dark matter, clusters would fly apart, unable to maintain their structure over cosmic time. The universe, it seems, is built upon something we cannot see. When scientists began estimating how much dark matter must exist, the result was unsettling. Dark matter appears to outweigh normal matter by a factor of roughly 5 to 1. Everything familiar, stars, planets, gas, dust, and life itself, makes up only a small fraction of the universe's total mass. This means that most of the universe is fundamentally invisible. It does not glow, it does not shimmer, it does not announce itself. It silently shapes galaxies, guides cosmic evolution, and dominates gravitational dynamics on the largest scales. Understanding what dark matter is has become one of the central challenges of modern physics. Importantly, dark matter is not simply ordinary matter that is hidden. Extensive searches have ruled out explanations involving faint stars, rogue planets, black holes in sufficient numbers, or clouds of gas. These possibilities cannot account for the observed effects without contradicting other measurements. Dark matter must be something else. One defining characteristic of dark matter is that it interacts extremely weakly with everything except gravity. It passes through ordinary matter almost without notice. Trillions of dark matter particles may pass through your body every second, leaving no trace. This ghostly behavior makes detection extraordinarily difficult. Traditional instruments rely on interactions with light or matter. Dark matter avoids both. To find it, scientists have built detectors deep underground, shielded from cosmic radiation, hoping to catch the rare moment when a dark matter particle interacts with an atomic nucleus. Others search for subtle signals in space that might arise from dark matter annihilation or decay. So far, these efforts have yielded tantalizing hints, but no definitive confirmation. Several theoretical candidates exist, each rooted in extensions of known physics. These candidates differ in mass, behavior, and interaction strength. What unites them is the attempt to reconcile cosmic observations with fundamental theory. Some models propose particles that were produced in enormous numbers during the early universe, lingering today as relics of cosmic history. Others suggest entirely new frameworks that alter how gravity behaves on large scales. At present, no single explanation has been conclusively proven. This uncertainty does not weaken the case for dark matter's existence. On the contrary, the evidence for its gravitational effects is overwhelming. What remains unknown is its identity. This distinction is important. Dark matter is not a placeholder for ignorance. It is a description of observed phenomena that demand explanation. The mystery lies not in whether it exists, but in what it is. Dark matter plays a crucial role in cosmic structure formation. In the early universe, slight variations in density were amplified by gravity. Dark matter, being unaffected by radiation pressure, began clumping early, forming scaffolds into which ordinary matter later fell. Without dark matter, galaxies may never have formed at all. In this sense, dark matter is responsible for the very existence of stars, planets, and eventually, life. It shaped the cosmic web, the vast filaments and voids that define the universe's large-scale structure. This web is not random. It is a direct consequence of how dark matter responds to gravity over billions of years. Seen from this perspective, the visible universe is merely decoration atop a hidden framework. What we see is guided by what we cannot. This idea challenges the human tendency to equate visibility with importance. The universe reminds us that influence does not require appearance. Despite its dominance, dark matter remains elusive in laboratories. This disconnect between cosmic certainty and experimental ambiguity is one of the most fascinating tensions in modern science. It forces physicists to question assumptions, refine theories, and explore new possibilities. It also highlights the limits of current knowledge without undermining confidence in the scientific method itself. Science advances not by pretending mysteries do not exist, but by confronting them honestly. Dark matter is a reminder that the universe operates on rules that are not always intuitive. It does not owe us simplicity. It reveals itself slowly, indirectly, and often reluctantly. There is a quiet elegance in this restraint. The universe does not give up its secrets easily. It demands patience, creativity, and humility. As detection efforts continue, scientists remain cautious. Claims require extraordinary evidence. Hints are scrutinized. Results are replicated. The goal is not speed, but certainty. Whether dark matter turns out to be a new particle, a modification of gravity, or something not yet imagined, its discovery will reshape our understanding of reality. And yet, even that discovery will not end mystery. Every answer in cosmology opens new questions. What properties does dark matter have? How did it form? Does it interact with itself? Does it influence the fate of the universe? Mystery is not a problem to be eliminated. It is the engine of inquiry. As we drift deeper into the universe's unseen components, we approach another enigma, even more perplexing. One that does not merely add mass, but alters the expansion of space itself. Unlike dark matter, this force does not pull inward. It pushes outward. It accelerates the universe. In the next part, we will explore dark energy, the phenomenon driving cosmic expansion faster and faster, challenging everything we thought we understood about gravity, space, and destiny. For much of the 20th century, astronomers believed they understood the broad fate of the universe. Gravity, the force that draws matter together, was assumed to be slowing cosmic expansion. The universe began in a hot, dense state and expanded outward, but over time, gravity would gradually reduce that expansion. The only remaining question was how strong the braking force would. Would the universe eventually stop expanding and collapse back inward, or would it coast outward forever, slowing but never reversing? This expectation felt reasonable. Gravity was familiar. It pulled apples downward and planets into orbit. On cosmic scales, it shaped galaxies and clusters. There was no obvious reason to suspect that the universe behaved differently on the largest scales. Then the measurements arrived. In the late 20th century, astronomers began studying distant exploding stars known as supernovae. These stellar explosions shine with remarkable consistency, allowing their intrinsic brightness to be estimated by comparing how bright they appear from Earth to how bright they are known to be. Astronomers can determine their distance. When these distances were compared to how fast their host galaxies were moving away, the results were unexpected. The universe was not slowing down. It was speeding up. Distant galaxies were receding faster than expected, as if some unknown influence were pushing space itself outward. The farther away a galaxy was, the faster it appeared to be accelerating away from us. This discovery was not subtle. It contradicted decades of assumptions and required a profound shift in cosmological thinking. The force responsible for this acceleration became known as dark energy. Like dark matter, dark energy is defined by what it does, not by what it is. Unlike dark matter, which pulls inward through gravity, dark energy appears to exert a repulsive effect, driving space apart. It does not clump. It does not form structures. It does not concentrate around galaxies. Instead, it seems to be a property of space itself, present everywhere, evenly distributed. As the universe expands, more space comes into existence, and with it, more dark energy. This creates a feedback loop. Expansion produces more dark energy, which drives further expansion. The implications are unsettling. If dark energy continues to dominate, the universe will not merely expand forever. It will expand faster and faster, pushing galaxies beyond each other's reach, thinning matter until stars exhaust their fuel and darkness deepens. This is not a dramatic explosion or collapse. It is a slow, quiet fading. A universe stretched thin by its own growth. Dark energy now appears to make up roughly 70% of the universe's total energy content. Dark matter contributes about 25%. Everything familiar, stars, planets, gas, dust, and life, accounts for only about 5%. The universe, as it turns out, is mostly composed of things we do not understand. Unlike dark matter, which reveals itself through gravitational clumping, dark energy reveals itself only through its effect on expansion. It does not interact with matter in any known direct way. It does not bend light. It does not leave traces in detectors. Its presence is inferred from the behavior of the universe as a whole. One way to think about dark energy is to imagine space as having an intrinsic tension, a tendency to stretch. This tension was negligible when the universe was small and dense, but as space expanded and matter thinned out, dark energy became dominant. In the early universe, gravity won. Matter was dense enough to slow expansion. Over time, as galaxies drifted apart, gravity weakened on large scales. Dark energy took over. This shift marks a turning point in cosmic history. The universe transitioned from matter-dominated to dark energy-dominated expansion. The nature of dark energy remains one of the deepest mysteries in physics. One possibility is that dark energy is a property of the vacuum itself. According to quantum physics, empty space is not truly empty. It seethes with fleeting fluctuations, particles appearing and disappearing too quickly to be observed directly. These fluctuations contribute energy. In theory, this vacuum energy could act as a repulsive force, driving expansion. However, when physicists attempt to calculate the expected value of vacuum energy, the result is catastrophically wrong. The predicted value exceeds observations by an enormous factor. This mismatch is one of the worst discrepancies between theory and observation in all of science. Another possibility is that dark energy represents a new field permeating space and evolving slowly over time. Such a field would influence expansion without interacting strongly with matter. This idea remains speculative and unproven. Some researchers have explored the possibility that gravity itself behaves differently on the largest scales. In these models, what appears as dark energy may be a sign that our understanding of gravity is incomplete. At present, none of these explanations has been confirmed. What makes dark energy particularly challenging is its subtlety. It does not announce itself through dramatic events. It reveals itself only through long-term trends measured across billions of years. To detect it, astronomers must observe vast numbers of galaxies, map cosmic structure, and measure expansion with extraordinary precision. Small uncertainties accumulate. Large datasets are required. Despite this difficulty, the evidence for accelerated expansion is strong and consistent across multiple independent measurements. The universe is not only expanding, it is accelerating. This acceleration changes how we think about cosmic destiny. In a dark energy-dominated universe, distant galaxies will eventually recede beyond visibility. Their light will stretch to wavelengths too long to detect. The observable universe will shrink, not because it becomes smaller, but because less of it remains accessible. Future observers, billions of years from now, may see only their local galaxy group, isolated in darkness with no visible evidence of a larger cosmos beyond. This possibility carries a quiet irony. We live at a time when the universe is still visible on grand scales. The cosmic background radiation remains detectable. Distant galaxies still reveal their motion. The universe still tells its story to those who listen. This era will not last forever. Dark energy ensures that the universe is changing not just in structure, but in what can be known. The acceleration of expansion also raises questions about the beginning of the universe. If expansion is accelerating now, what governed expansion in the past? How did dark energy behave in earlier epochs? Has it always existed in the same form? These questions remain open. What is clear is that dark energy challenges intuition. It behaves unlike any force encountered in daily life. It does not pull objects apart locally. It does not tear atoms or planets apart. Its influence emerges only over vast distances and long times. This scale dependence makes dark energy both elusive and profound. It is a reminder that the universe operates on rules that only become visible when viewed as a whole. Dark energy also reshapes the emotional landscape of cosmology. Earlier models offered dramatic endings, collapse, rebirth, cycles. Dark energy suggests a quieter fate, not destruction, but isolation. Not explosion, but dilution. Whether this future is truly inevitable depends on what dark energy turns out to be. If its strength changes over time, the story could evolve differently. But for now, acceleration appears steady. Science approaches this mystery cautiously. Measurements are refined, models are tested, observations are compared across methods. The universe is under no obligation to conform to expectations. As with dark matter, dark energy teaches humility. It reminds us that what we understand may be only a surface layer atop deeper realities. We have measured the expansion of space. We have confirmed its acceleration. But we do not yet know why it happens. And in that not knowing lies both frustration and beauty. The universe continues to expand, carrying galaxies apart, stretching space-time itself, while leaving behind questions that echo across billions of light years. In the next part, we will turn our attention to regions where gravity overwhelms expansion completely, places where space-time curves so sharply that even light cannot escape. There, in the depths of collapsed stars, the laws of physics are pushed to their limits. This is where the universe grows most extreme. There are places in the universe where expansion gives way to collapse, where gravity does not merely guide motion, but overwhelms it, where matter is compressed beyond familiar states, and the rules that govern everyday reality begin to strain under extreme conditions. These places are known as black holes. For much of the 20th century, black holes existed only as mathematical curiosities. Equations suggested their possibility, but their reality remained uncertain. The idea that matter could collapse so completely that not even light could escape seemed implausible, almost poetic rather than physical, and yet observation slowly confirmed what theory had predicted. Black holes form when gravity wins absolutely. When a massive star exhausts its nuclear fuel, it can no longer support itself against its own weight. The outward pressure generated by fusion fades, and gravity takes control. The star collapses inward, compressing matter to extraordinary densities. If the remaining mass is large enough, nothing halts the collapse. The result is a region of space where gravity becomes so intense that escape is impossible. The boundary surrounding this region is called the event horizon. Once crossed, all paths forward lead inward. The event horizon is not a physical surface. It is not a wall or barrier. It is a boundary defined by motion. Inside it, every possible trajectory leads deeper into the black hole. Outside it, escape remains possible. From a distance, a black hole behaves like any other object with mass. It exerts gravity. It influences orbits. It shapes nearby motion. There is nothing inherently destructive about its presence. Danger arises only when objects venture too close. As matter approaches a black hole, it does not vanish instantly. It spirals inward, forming a rotating disk of gas and debris. Friction and compression heat this material to extreme temperatures, causing it to glow brightly. In this way, black holes often reveal themselves indirectly. They announce their presence not through darkness, but through intense radiation emitted by infalling matter. Some of the most luminous objects in the universe are powered by black holes. At the centers of galaxies, supermassive black holes consume material and release vast amounts of energy. These active regions can outshine entire galaxies. The existence of supermassive black holes raises questions that remain unresolved. How did they grow so large so early in cosmic history? Did they form from the collapse of massive stars or through direct collapse of gas clouds? Did smaller black holes merge over time? Observations show that nearly every large galaxy hosts a supermassive black hole at its center. Our own galaxy contains one, with a mass millions of times greater than that of the Sun. It remains relatively quiet, but its gravitational influence shapes the surrounding region. Black holes come in different sizes. Stellar mass black holes form from collapsing stars and weigh several times the mass of the Sun. Supermassive black holes weigh millions or billions of times more. Between these extremes lie intermediate mass black holes, whose existence is supported by growing evidence, but not yet fully understood. What unites all black holes is the extreme curvature of spacetime they produce. According to general relativity, mass tells spacetime how to curve, and spacetime tells matter how to move. Black holes represent the most extreme application of this principle. Near them, spacetime bends so sharply that conventional intuition fails. Time itself behaves strangely near a black hole. To a distant observer, objects approaching the event horizon appear to slow down, their motion stretched and reddened. They never seem to cross the horizon, fading gradually from view. To the falling object, however, nothing unusual occurs at the boundary. The crossing happens without fanfare. This difference in perception highlights the relative nature of time and observation. Inside the event horizon, physics becomes uncertain. At the center lies what is called a singularity, a region where density and curvature appear to become infinite. Current theories break down here. Equations lose meaning. Predictions fail. The singularity is not necessarily a physical point in the conventional sense. It is a signal that our understanding is incomplete. This breakdown is not limited to black holes. It also appears when describing the earliest moments of the universe. In both cases, extreme conditions expose the limits of current theories. Black holes therefore serve as natural laboratories for fundamental physics. They push gravity, quantum mechanics, and space-time to their extremes, revealing tensions between theories that otherwise work well independently. One of the most famous puzzles associated with black holes concerns information. According to quantum mechanics, information cannot be destroyed. The details of a system's state must always be preserved, even if scrambled beyond recognition. But black holes seem to erase information completely. Anything that falls in appears lost forever. This conflict between quantum theory and black hole physics led to the information paradox. If black holes destroy information, quantum mechanics must be incomplete. If information is preserved, then our understanding of black holes must change. Decades of debate have produced insights, but no final resolution. Some theories suggest that information is encoded on the event horizon. Others propose subtle correlations in radiation emitted by black holes. This radiation, predicted by quantum effects near the horizon, implies that black holes are not entirely black. Over immense timescales, they can lose mass and eventually evaporate. This process is extraordinarily slow for astrophysical black holes, far exceeding the current age of the universe. Nevertheless, it introduces the idea that black holes evolve rather than remaining eternal. Black hole mergers offer another window into extreme physics. When two black holes spiral together and merge, they release energy in the form of gravitational waves. These ripples in space-time propagate outward, carrying information about the collision. The detection of gravitational waves confirmed a major prediction of relativity and opened a new way of observing the universe. Through these signals, scientists can study events invisible to traditional telescopes. Gravitational wave observations have revealed populations of black holes previously unknown. They have measured masses, spins, and merger rates, expanding understanding of stellar evolution and cosmic history. These observations also reinforce the reality of black holes. They are no longer theoretical constructs. They are observed entities, shaping the universe in measurable ways. Despite this progress, black holes remain deeply mysterious. What happens to matter inside them? How does space-time behave near singularities? How do quantum effects modify gravity under such conditions? These questions remain unanswered. Black holes challenge the idea that the universe is fully understandable through existing frameworks. They reveal that even well-tested theories have domains where they fail. This failure is not discouraging. It is instructive. Science advances by identifying where understanding breaks down. Black holes mark these boundaries clearly. They point toward new physics, waiting to be discovered. On a more human level, black holes provoke awe and unease. They embody extremes of power and invisibility. They remind us that the universe contains regions far removed from everyday experience. And yet, black holes are not monsters lurking in space. They are consequences of gravity, following the same laws that govern falling apples and orbiting planets, extended to their limits. They do not roam the universe devouring stars indiscriminately. They occupy specific regions, interacting with their surroundings in predictable ways. In this sense, black holes are less terrifying than they are revealing. They show us that the universe allows extremes, that reality is not constrained by comfort or familiarity, that nature explores possibilities far beyond human-scale phenomena. As we continue to observe and model black holes, we refine our understanding of gravity, time, and space. Each discovery sharpens the questions that remain. Black holes stand at the intersection of what we know and what we do not. They are not the end of inquiry, but a doorway into deeper understanding. In the next part, we will move away from collapsed stars and extreme gravity and turn toward a more subtle mystery. We will examine time itself, not as a clock on a wall, but as a dimension woven into the fabric of the universe. We will explore how time behaves differently across space, how it stretches and compresses, and why its flow remains one of the most profound, unanswered questions in science. Time feels simple in daily life. It moves forward. Seconds follow seconds. Causes precede effects. Memories collect behind us while the future remains unknown. This steady progression is so familiar that it rarely invites scrutiny. Yet when examined closely, time becomes one of the universe's most profound mysteries. Modern physics reveals that time is not separate from space. It is woven together with it, forming a unified structure known as space-time. This idea reshaped how scientists understand motion, gravity, and causality. Before this realization, space was thought of as a static stage on which events unfolded, and time as a universal clock ticking uniformly everywhere. That view no longer holds. According to relativity, time does not flow at the same rate for all observers. It stretches and compresses depending on motion and gravity. Two clocks moving differently or experiencing different gravitational environments will measure time differently. These effects are not theoretical curiosities. They have been measured repeatedly. Clocks aboard satellites tick at slightly different rates than clocks on Earth. Without accounting for these differences, navigation systems would fail. Time, it turns out, this flexibility becomes extreme near massive objects. Gravity slows time. The stronger the gravitational field, the more slowly time passes relative to distant observers. Near a black hole, this effect becomes dramatic. An observer far away might see time near the event horizon nearly freeze. For someone falling inward, their own time would feel normal. while the rest of the universe appears to speed up. This difference in perception challenges the idea of a single, shared present moment. There is no universal now that applies everywhere. What is simultaneous for one observer may not be simultaneous for another. Events separated by vast distances can be ordered differently, depending on perspective. This does not create contradiction. It reveals that simultaneity itself is relative. The universe does not provide a master clock. Each observer carries their own. This insight reshapes how we think about causality. While cause must still precede effect within an observer's frame, the ordering of distant events can vary without violating physical laws. Time becomes local rather than absolute. Despite this flexibility, time still appears to flow in one direction. We remember the past, not the future. Systems evolve from order to disorder. Eggs break but do not unbreak. Smoke disperses but does not gather itself back into flame. This directionality is known as the arrow of time. The arrow of time is closely associated with entropy, a measure of disorder. In isolated systems, entropy tends to increase. This statistical tendency gives time its apparent direction. On microscopic scales, the fundamental laws of physics are largely time-symmetric. They do not prefer a direction. But when many particles interact, statistical behavior emerges, producing irreversible processes. This raises a deep question. If the laws of physics do not distinguish past from future, why does time feel directional? One answer lies in the initial conditions of the universe. The early universe appears to have been in an extraordinarily low entropy state. As it evolved, entropy increased, creating the arrow of time we experience. Why the universe began in such a low entropy condition remains unknown. This question connects time to cosmology itself. The flow of time may be inseparable from the universe's origin and evolution. In this sense, time is not merely a backdrop. It is a dynamic participant in cosmic history. Time also behaves differently across scales. On quantum scales, time is treated differently than in relativity. Reconciling these approaches remains an open challenge. Quantum mechanics treats time as an external parameter. Relativity treats it as part of space-time, influenced by matter and energy. Unifying these views is one of the central goals of theoretical physics. Until such a theory is developed, time remains conceptually divided. Another mystery concerns whether time could exist without change. Is time meaningful if nothing happens? Does time require events, or do events require time? These questions blur the line between physics and philosophy, yet they arise naturally from scientific inquiry. Cosmic time introduces further complexity. When astronomers describe the age of the universe, they refer to time measured by observers who move with the cosmic expansion. This provides a useful reference frame, but it is not universal in an absolute sense. Different observers experience different elapsed times since the universe's beginning, depending on their motion and location. Even the idea of a beginning raises questions. Time appears to have emerged with the universe itself. Asking what came before may be meaningless if time did not yet exist. This challenges intuition. In everyday life, every event has a before. In cosmology, the concept may break down. The boundary where time begins is not a wall, but a limit of description. Our equations work up to a certain point. Beyond that, they lose meaning. Time may not be fundamental. Some theories suggest it could emerge from deeper processes, much as temperature emerges from the collective motion of particles. If so, Time as we experience it may be an approximation, valid at large scales but not at the deepest levels of reality. This possibility remains speculative, but it highlights how much remains unknown. Despite these uncertainties, time remains a practical tool. It orders events, allows prediction, and underpins causality. Without it, science would be impossible. Yet the universe reminds us that time is not as simple as it seems. It bends near massive objects. It flows differently for different observers. It emerges from conditions that remain mysterious. Time also connects intimately with memory and identity. Our sense of self is tied to continuity through time. We experience change because time allows difference. In the universe, time allows evolution. Stars are born, live, and die. Galaxies form and collide. Structures emerge and dissolve. Without time, the universe would be static, unchanging, and unknowable. And yet, time also erases. It smooths structures, disperses energy, and carries the universe toward greater entropy. This dual role makes time both creative and destructive. As we gaze into space, we observe time in action. We see stars at different stages of life. We see galaxies evolving. We see remnants of ancient explosions. The universe presents itself not as a snapshot, but as a story unfolding across billions of years. Time is the thread that connects these moments. Understanding time fully may require new ideas, new mathematics, and new experiments. It may demand a revision of assumptions held for centuries. For now, time remains one of the universe's deepest mysteries. In the next part, we will turn toward the question of beginnings. We will explore what science can say about the origin of the universe, what evidence supports current models, and where certainty ends. We will examine how the universe began, and why that beginning remains both well-supported and profoundly incomplete. Every mystery in cosmology eventually leads back to the same question. Where did it all come from? Not just stars and galaxies, but space itself, time itself, the conditions that allowed anything to exist at all. Modern science approaches this question carefully. It does not claim to explain creation in a philosophical or metaphysical sense. Instead, it traces the universe's history backward using observation, measurement, and theory, stopping only where evidence runs out. The most successful framework for describing the universe's early history is known as the Big Bang Theory. Despite its name, the Big Bang was not an explosion in space. It was an expansion of space. The universe did not erupt outward from a single point into emptiness. Instead, space itself began expanding everywhere at once. This distinction matters. When astronomers observe galaxies moving away from one another, they are not seeing debris flying outward from a central blast. They are witnessing space stretching, carrying galaxies along with it. The evidence for this expansion is strong and multifaceted. One of the most important pieces is the cosmic microwave background. This faint radiation fills the universe almost uniformly. It is the cooled remnant of a time when the universe was hot, dense, and opaque. In the early universe, matter and radiation were tightly coupled. Light could not travel freely. As the universe expanded and cooled, it reached a point where atoms could form, allowing light to move unhindered. That light has been traveling ever since, stretched to microwave wavelengths by expansion. The cosmic microwave background provides a snapshot of the universe at a very early stage. Its uniformity and subtle variations match predictions with remarkable precision. Another line of evidence comes from the abundance of light elements. Calculations of nuclear reactions in the early universe predict specific ratios of hydrogen, helium, and lithium. Observations align closely with these predictions. Together, these observations form a coherent picture. The universe began hot and dense, then expanded and cooled, allowing structure to emerge. Yet even within this successful framework, mystery remains. The Big Bang Theory describes what happened after the universe began expanding. It does not explain why the universe began expanding or what caused the initial conditions. When equations are run backward, they point toward an early state of extreme density and temperature. At a certain point, known as the Planck time, current theories break down. Beyond this boundary, predictions lose meaning. This is not a failure of the theory. It is an honest acknowledgement of its limits. Some models propose a brief period of extremely rapid expansion early in cosmic history. This idea, known as inflation, helps explain why the universe appears so uniform and why distant regions share similar properties. Inflation remains an active area of research. While it fits many observations, details about how it occurred and what drove it remain uncertain. What came before inflation, if anything, is unknown. Some theories suggest the universe may have undergone cycles of expansion and contraction. Others propose that our universe is one of many. These ideas remain speculative and are not confirmed by direct evidence. Science treats such possibilities cautiously. What is known is that time itself appears to have emerged with the universe. Asking what happened before the Big Bang may be like asking what lies north of the North Pole. The question may not apply. This challenges intuition deeply. Human experience is rooted in sequence. We expect every event to have a cause, but causality may not extend beyond the universe's origin in the way we imagine. The beginning of the universe is not just a scientific puzzle. It touches the limits of explanation itself. Yet even within these limits, science has achieved something extraordinary. It has traced cosmic history from the first fractions of a second through billions of years of evolution, guided by evidence rather than assumption. The universe's beginning remains mysterious, not because we lack imagination, but because nature sets boundaries on what can be observed. In this sense, the mystery is not a gap to be filled recklessly. It is a frontier to be respected. As we shift from origins to possibility, another question arises naturally. If the universe has existed for billions of years, if it contains countless galaxies and planets, then what about life? Is life unique to Earth, or is it a common outcome of cosmic evolution? This question carries both scientific and emotional weight, and it leads us into the next mystery. The question of life beyond Earth is one of the most quietly powerful questions humans ask. It does not demand spectacle. It does not require drama. It rests on simple curiosity. In a universe so vast, could life truly exist in only one place? For most of history, this question belonged to philosophy. Today, it belongs increasingly to science. Astronomers have confirmed that planets are common. Nearly every star appears to host planetary systems. Many of these planets exist in regions where conditions could allow liquid water to persist. These discoveries transformed speculation into investigation. Life as currently understood requires specific conditions, energy sources, chemical complexity, stable environments. Liquid water appears to be especially important. Earth provides one example, not a template. The universe offers countless variations. Some planets orbit close to their stars, locked in eternal daylight or darkness. Others orbit far away, cold and dim. Some moons orbit giant planets, warmed by tidal forces rather than sunlight. Life does not require familiarity. It requires opportunity. The search for life focuses first on simple forms. Microbial life is more resilient and adaptable than complex organisms. If life exists elsewhere, it may not announce itself dramatically. Detecting life across interstellar distances is extraordinarily difficult. Scientists look for indirect signs, atmospheric gases that should not coexist, chemical imbalances that suggest biological processes. These signatures are subtle and require careful interpretation. At the same time, the search for technological civilizations continues. Radio telescopes scan the sky for artificial signals. Thus far, the universe remains silent. This silence is itself a puzzle. If intelligent life is common, why do we see no evidence? If it is rare, why did it arise here? Possible explanations range from the fragility of life to the brief duration of technological phases. None are confirmed. The universe may be full of life at scales and forms we do not recognize, or it may be largely empty. Both possibilities carry profound implications. Life connects cosmology to biology, chemistry, and consciousness. It reminds us that the universe is not just structure and motion, but complexity, capable of awareness. Whether awareness exists elsewhere remains unknown. What is certain is that the universe permits life, at least once. That fact alone is remarkable. As we look outward, we are also looking inward. We are asking not only where life exists, but what life is. In the vastness of the cosmos, Earth is small, but significance is not measured by size. The universe produced beings capable of asking questions about its origin, structure, and fate. That may be rare, or it may be common. For now, the mystery remains open. When we look far enough into the universe, distance turns into time. When we look far enough into time, the future becomes as mysterious as the past. The universe does not stand still. It evolves, it expands, it cools, it changes in ways both subtle and dramatic. And just as science traces the universe backward toward its beginning, it also projects forward, asking what lies ahead. The future of the universe is not a single story with a single ending. It is a set of possibilities shaped by forces we are still struggling to understand. At the center of these possibilities lies expansion. The universe is growing larger. Galaxies drift apart. Space stretches between clusters. Over time, this expansion alters everything, from the structure of galaxies to the fate of stars themselves. If dark energy continues to behave as it does now, expansion will dominate the universe's future indefinitely. In this scenario, gravity slowly loses its ability to pull distant structures together. Galaxy clusters drift apart. Interactions become rarer. The universe grows quieter. Stars continue to form for a time, but eventually, the raw material required for star formation is exhausted. Gas clouds thin. Stellar birth slows, then stops. The universe enters an era defined not by creation, but by aging. Existing stars burn through their fuel. Massive stars live briefly and explode. Smaller stars burn slowly, glowing faintly for trillions of years. Over time, even these long-lived stars fade. Galaxies grow dim. What remains are stellar remnants. White dwarfs, neutron stars, black holes, objects that no longer shine, drifting through expanding space. This future is sometimes described as heat death, not because everything becomes hot, but because usable energy becomes evenly distributed. Differences fade, Processes that depend on gradients can no longer operate. The universe becomes cold, dark, and diffuse. This is not an ending marked by violence or collapse. It is a gradual thinning, a quiet stretching, a slow fading of structure. Yet even in this far future, change does not cease entirely. Black holes continue to interact with their surroundings. Over unimaginably long timescales, they lose mass through quantum effects. Eventually, even they evaporate. What remains afterward is difficult to imagine. A universe dominated by low-energy particles, radiation stretched thin by expansion, drifting endlessly. This vision of the future is based on current understanding. It is not a certainty. If dark energy behaves differently over time, the story could change. Expansion might slow. It might reverse. It might intensify dramatically. Some models suggest a future where expansion accelerates so rapidly that even atoms are torn apart. Others suggest long-term stability, punctuated by rare events. Science cannot yet distinguish between these possibilities. The uncertainty does not weaken cosmology. It defines its frontier. The future of the universe depends on forces that operate subtly, shaping reality over billions of years. Measuring these forces requires patience, precision, and humility. What is striking is how indifferent the universe appears to human timelines. Civilizations rise and fall in moments too brief to matter cosmically. Entire species emerge and vanish without leaving detectable traces. The universe continues, largely unaffected. And yet, within this indifference lies something extraordinary. The universe has produced observers. It has produced minds capable of contemplating cosmic history and cosmic fate, of measuring expansion, of detecting faint radiation left over from the earliest moments of time. This capacity for understanding may be rare, or it may be common. We do not yet know. What we do know is that curiosity itself is a product of cosmic evolution. The atoms in your body were forged in stars. The elements that make thought possible were scattered by ancient explosions. The same universe that stretches galaxies apart also assembled the conditions for awareness. In this way, the universe is not separate from the observer. It is expressed through them. This realization reframes the question of meaning. Meaning does not need to be imposed on the universe from outside. It arises naturally when complexity reaches a level capable of reflection. The universe may not care whether it is understood, but it allows itself to be understood. That allowance is remarkable. Throughout this journey, we have explored mysteries that span the visible and the invisible. Dark matter shaping galaxies without revealing itself. Dark energy driving expansion without explanation. Black holes warping space-time beyond intuition. Time flowing unevenly across the cosmos. Origins hidden behind physical limits. Life uncertain but possible. Each mystery remains unresolved, not because science has failed, but because nature is deep. Mystery is not a flaw in understanding. It is the condition that makes understanding possible. Every answer reshapes the questions that follow. The universe does not yield a final explanation. It offers layers, patterns, boundaries, invitations to look closer. And perhaps that is enough. As the universe continues to expand, as stars continue to burn, and as questions continue to echo, one truth remains steady. We are part of this story. Not separate from it, not central to it, but woven into it. To study the universe is to study the conditions that made study possible at all. To wonder about its future is to acknowledge our brief presence within it and to rest beneath its vastness. Listening to its quiet rhythms is to reconnect with a perspective older than history. The universe does not rush, it unfolds. And in its unfolding, it leaves room for curiosity, for humility, and for awe. If you've enjoyed drifting through these mysteries, and if you find calm in exploring the vast questions of existence, consider supporting the channel. Like the video if it helped you relax. Subscribe if you'd like more quiet journeys through science, space, and the unknown. And as you rest, remember this: you are made of the same universe you are trying to understand. When the universe is viewed from far enough away, individual galaxies fade into insignificance. What emerges instead is structure. Not random scatter, not uniform fog, but an intricate pattern stretching across billions of light years. A vast arrangement of filaments, knots, and empty regions that together form what astronomers call the cosmic web. This structure was not designed. It was not planned. It emerged naturally from gravity acting over immense spans of time. In the early universe, matter was distributed almost evenly, with only tiny fluctuations in density. These fluctuations were minute, barely noticeable, yet they mattered. Gravity amplified them relentlessly. Regions slightly denser than their surroundings pulled in more matter. Regions slightly emptier lost matter. Over billions of years, these differences grew until the universe developed a large-scale skeleton. Along this skeleton lie filaments of galaxies stretching across space like luminous threads. Where filaments intersect, galaxy clusters form, the densest nodes in the cosmic web. Between these structures lie vast voids, regions containing almost nothing at all. These voids are not small gaps. Some span hundreds of millions of light years. The universe, on its largest scales, resembles a sponge or foam, where matter outlines the edges and emptiness dominates the interior. This realization changed cosmology profoundly. For centuries, the universe was imagined as either uniform or chaotic. The discovery of the cosmic web revealed order on scales far beyond anything previously imagined. This structure is not visible in a single glance. It emerges only when thousands or millions of galaxies are mapped together. Each galaxy is a point. Together, they trace a pattern. The pattern tells a story. It reveals how dark matter shaped the universe long before stars existed. Dark matter collapsed first, forming the scaffolding into which ordinary matter later fell. Galaxies formed where dark matter was densest, lighting up an invisible framework. In this way, the visible universe is an outline of something unseen. The cosmic web also explains why galaxies are not distributed evenly. They form along filaments because gravity funnels matter there. They avoid voids because those regions lost material early on. Even today, galaxies drift slowly along these filaments, drawn toward clusters, merging and interacting over immense timescales. This motion is not dramatic. It unfolds over billions of years, yet it shapes the future of cosmic structure. The web itself continues to evolve. Expansion stretches it. Dark energy pushes clusters apart. Over time, filaments thin and connections weaken. Eventually, if expansion continues unchecked, the web will unravel. Understanding the cosmic web requires simulations of staggering complexity. Scientists model billions of particles, tracking how gravity pulls matter into shape over cosmic time. These simulations reproduce observed structures with remarkable accuracy. lending confidence to current models. Yet even here, mysteries remain. Why did the initial fluctuations have the specific patterns observed? Why do voids have their particular sizes? Why does structure form in exactly this way and not another? These questions trace back to the universe's earliest moments. The cosmic web also reframes humanity's place in the universe. Our galaxy resides within a filament, part of a larger supercluster, connected to countless others across space. We are not isolated. We are part of a vast network shaped by forces far older than Earth. This perspective invites humility. It also invites wonder. The universe is not just large. It is organized. It contains architecture without intention, design without a designer, structure without planning. Gravity, acting patiently, produced complexity on scales that dwarf imagination. And this complexity remains incomplete. Even now, scientists refine maps of the cosmic web, extending them deeper into space, further back in time. Each new survey reveals structure where once there was only darkness. The universe continues to reveal its shape slowly, reluctantly, one observation at a time. Black holes represent one extreme outcome of gravity. But they are not the only places where the universe presses matter to its limits. Between ordinary stars and complete collapse lies another class of objects, smaller than black holes, denser than anything else known to exist, and governed by physics that pushes theory to the brink. These are neutron stars. A neutron star forms when a massive star dies, but not quite violently enough to become a black hole. When nuclear fuel is exhausted, gravity overwhelms the star's internal pressure, and the core collapses. Protons and electrons are forced together, combining into neutrons. The result is a sphere composed almost entirely of neutrons, packed unimaginably tightly. The collapse happens rapidly. In a matter of seconds, a stellar core, larger than a city, is compressed into a sphere only about 20 kilometers across. The density is extreme. A single teaspoon of neutron star material would weigh billions of tons under Earth's gravity. Matter is compressed so tightly that atomic structure collapses. Electrons no longer orbit nuclei. Atoms cease to exist as distinct entities. Instead, matter becomes something unfamiliar. A dense quantum fluid governed by forces that rarely dominate under ordinary conditions. Neutron stars sit at the boundary between what physics understands and what it does not. They are held up not by heat like ordinary stars, but by quantum pressure. Neutrons resist being squeezed into the same state, creating a force strong enough to counter gravity up to a point. That point is known as the neutron star mass limit. If a neutron star grows too massive, perhaps by stealing material from a companion star or merging with another neutron star, even quantum pressure fails. Gravity wins. Collapse resumes. The star becomes a black hole. This threshold marks a boundary in nature. On one side lies matter in its densest stable form. On the other lies complete gravitational collapse. Understanding what happens inside neutron stars is one of the hardest problems in modern physics. Their interiors are inaccessible. No probe can enter. No signal carries direct information from their cores. Everything scientists know comes from indirect observation and theoretical modeling. Neutron stars rotate rapidly. Some spin hundreds of times per second. As they rotate, they emit beams of radiation from their magnetic poles. When these beams sweep past Earth, They appear as regular pulses. These objects are called pulsars. Pulsars are among the most precise natural clocks in the universe. Their pulses arrive with astonishing regularity. Deviations as small as fractions of a second over years can be detected. This precision allows pulsars to be used as laboratories for testing fundamental physics. They reveal how matter behaves under extreme gravity, how space-time curves, and how magnetic fields evolve. Some neutron stars possess magnetic fields trillions of times stronger than Earth's. These magnetars can crack their own crusts, releasing bursts of energy detectable across the galaxy. The crust of a neutron star is itself exotic. It is thought to be a lattice of nuclei immersed in a sea of electrons and neutrons. Deeper layers may contain even stranger phases of matter, sometimes described using names borrowed from everyday objects, though the reality is far from familiar. Physicists propose that inside neutron stars, matter may organize into complex structures under competing forces: gravity, nuclear attraction, and quantum effects. These structures are theoretical, inferred from equations rather than observed directly. The uncertainty is profound. Different models predict different internal compositions. Some suggest that neutrons may break down into more fundamental particles. Others propose exotic states involving strange quarks. None have been confirmed. This ignorance is not due to lack of effort. It reflects the limits of experimentation. The pressures inside neutron stars exceed anything that can be reproduced in laboratories on Earth. Nature has already performed the experiment. We are left to observe from afar. Neutron star mergers offer rare glimpses into these extremes. When two neutron stars spiral together and collide, they release vast amounts of energy. Gravitational waves ripple outward. Matter is ejected at high speeds. Heavy elements are forged in the chaos. Gold, platinum, and other heavy elements are believed to be produced primarily in these violent events. The atoms in jewelry and electronics may owe their existence to ancient neutron star collisions. In this way, extreme astrophysics connects directly to everyday matter. The universe produces elements through violence, then distributes them quietly across space. Planets form from debris left behind. Life assembles itself from remnants of catastrophe. This continuity between the extreme and the familiar is one of the universe's most subtle themes. Neutron stars also challenge understanding of gravity itself. Their compactness makes relativistic effects strong. Time passes more slowly near their surfaces. Light is bent sharply. Orbits behave differently than intuition suggests. These effects can be measured. Observations of neutron star systems provide some of the most stringent tests of gravitational theory available. So far, predictions hold, but the margin for error is narrow. The moment gravity fails to match observation, new physics would be required. Beyond neutron stars lies a deeper question. Is there an ultimate limit to density? Do black holes represent an endpoint, or merely another phase in a deeper hierarchy of structure? Current theories suggest singularities, points where density becomes infinite. But infinities often signal breakdowns in theory rather than physical reality. Many physicists suspect that at extreme densities, new physics emerges. Quantum gravity effects may prevent true singularities from forming. Space-time itself may have a smallest scale. These ideas remain speculative. What is clear is that the universe allows matter to reach conditions utterly unlike anything on Earth. It does not avoid extremes. It explores them fully. Neutron stars stand as monuments to this willingness. They are small in size, rare in number, yet disproportionately important. They anchor theory at the edge of the known. They connect gravity, quantum mechanics, nuclear physics, and astrophysics in a single object. They remind us that the universe is not obligated to remain within human comfort zones. The deeper scientists probe these objects, the more questions arise. What is the true nature of matter at nuclear densities? How do forces behave when compressed beyond ordinary regimes? What prevents collapse, and why? These questions do not yet have answers, and that is precisely why neutron stars matter. They show that even after centuries of study, the universe retains domains that resist explanation. They expose gaps not in curiosity, but in knowledge. They stand between stars and black holes, between the familiar and the unknowable. In the next extension, we will move even further outward, not toward extreme matter, but toward extreme limitation. We will explore the boundaries of what can be observed, what can be known, and what the universe may permanently withhold from understanding. Some mysteries are unsolved. Others may be unsolvable. There is a boundary in the universe that no telescope can cross. Not because of distance alone, and not because of technological limitation, but because of the way reality itself is structured. This boundary is known as a horizon. In everyday life, a horizon is simply the limit of sight. On a flat plain or at sea, it marks where Earth curves away. In cosmology, horizons are far more profound. They define what can be known, what can be observed, and what will remain forever beyond reach. The most familiar of these is the cosmic horizon. Light travels at a finite speed. The universe has a finite age. Together, these facts impose a limit on observation. No signal from beyond a certain distance has had enough time to reach us. This means that the observable universe is not the entire universe. It is only the portion that has been able to communicate with us since cosmic expansion began. Beyond this horizon may lie more galaxies, more structure, perhaps infinitely more. But they are causally disconnected. Their light will never arrive. Their events will never influence us. This is not a temporary limitation. It is a permanent feature of space-time. Even if humanity survives for trillions of years, even if technology advances beyond current imagination, these regions will remain inaccessible. No amount of patience can overcome the speed of light. The universe contains information that is, in principle, unreachable. This realization marks a shift in how science understands knowledge itself. Science is powerful, but it is not omnipotent. It operates within boundaries set by physical law. Some questions may have answers that can never be observed or tested. This does not diminish science. It clarifies its scope. Beyond the cosmic horizon lies the question of whether the universe is finite or infinite. Observations suggest that space is very nearly flat, meaning it could extend without end. But because we can observe only a portion, certainty remains out of reach. An infinite universe would contain endless repetition. Every possible arrangement of matter would occur somewhere. This idea is unsettling, not because it is proven, but because it follows naturally from certain assumptions. Yet even this possibility cannot be confirmed. The horizon hides not only space, but history. As dark energy drives expansion, distant galaxies will gradually slip beyond view. Their light will stretch until it fades entirely. The observable universe will shrink, not physically, but informationally. Future observers may see a quieter sky than we do now. Fewer galaxies, less evidence of expansion. The cosmic microwave background will fade into undetectability. In that future, cosmology itself may become more difficult. This introduces a subtle irony. We live at a time when the universe still reveals much of its history. The early universe is still visible. Large-scale structure is still detectable. The expansion can still be measured. This era will not last forever. The universe does not guarantee that its story remains readable indefinitely. Another horizon exists closer to home. The particle horizon defines the farthest distance from which particles could have traveled to us since the universe began. Beyond it lies space that has never been in causal contact with our region. This raises questions about uniformity. Why does the universe appear so similar in all directions if distant regions were never connected? This puzzle led to ideas like inflation, which propose early mechanisms to explain uniformity. Whether inflation is correct in detail remains uncertain. But the question it addresses arises directly from horizon limits. Horizons also exist around black holes. The event horizon marks a boundary beyond which information appears lost. Once crossed, signals cannot escape. From the outside, the interior becomes unknowable. This challenges the idea that information is always preserved and accessible. It forces physicists to confront conflicts between theory and observation. Black hole horizons are local versions of a cosmic theme. There are places in the universe where knowledge stops, not gradually, abruptly. Beyond these boundaries, prediction gives way to silence. This does not mean reality ceases to exist there. It means interaction ceases. The universe contains regions that exist without reference to us. This realization alters how meaning is assigned. Human intuition often equates existence with observation. But cosmology teaches otherwise. Things can exist without ever being seen. Events can occur without ever being recorded. The universe is larger than its observers. Another limit arises from quantum mechanics. At extremely small scales, uncertainty becomes fundamental. Certain properties cannot be known simultaneously with arbitrary precision. This is not a measurement flaw, it is a feature of reality. When combined with gravity, this uncertainty suggests a smallest possible length scale. Below this scale, the concept of distance itself may lose meaning. If space-time is discrete at the smallest scales, then continuity is an approximation. The smooth fabric we perceive may emerge from something grainier underneath. This idea remains theoretical, but it hints at deeper limits on knowledge. Some questions may be unaskable, not because they lack answers, but because the framework required to ask them breaks down. There is also a computational limit to understanding. The universe processes information as it evolves. There are upper bounds on how much information can be stored within a given region. These limits are tied to area rather than volume, suggesting surprising connections between geometry and information. This implies that reality itself has an information budget. Not everything can be encoded arbitrarily. Not everything can be known simultaneously. Knowledge has a physical cost. Even consciousness may be subject to these limits. Human minds evolved to operate at certain scales, under certain conditions. While abstraction allows extension beyond intuition, it cannot eliminate cognitive constraints entirely. Some aspects of the universe may be understandable only mathematically, never intuitively. Others may resist even that. This does not mean inquiry should stop. It means expectations should adjust. The goal of cosmology is not to eliminate mystery. It is to understand structure, behavior, and boundaries as clearly as possible. Some mysteries resolve into explanations. Others remain open permanently. This permanence is not a failure. It is a property of a universe governed by laws that permit both clarity and concealment. The universe does not owe complete transparency, yet it reveals enough to sustain curiosity indefinitely. There will always be new measurements to refine, new theories to test, new patterns to uncover. Even within known limits, understanding can deepen endlessly. The edge of knowing is not a wall. It is a coastline. Exploration reshapes it continuously, even if the ocean beyond remains vast. In the quiet recognition of these limits, cosmology becomes something more than a technical discipline. It becomes a meditation on perspective. We are finite beings studying an immense reality from a small vantage point. We cannot step outside the universe to see it whole. We observe from within, tracing patterns from partial information. And yet, within this limitation, we have achieved remarkable insight. We have measured the age of the universe. We have mapped its structure. We have detected echoes from its earliest moments. We have identified forces that dominate its behavior, all while knowing that some answers will remain unreachable. This balance between knowledge and mystery is not discouraging, it is stabilizing. It grounds inquiry in humility and curiosity rather than certainty. The universe remains larger than our theories. And that is precisely what makes it worth studying. The universe does not speak in sentences. It does not hand over explanations in neat packages. It does not pause to make sure we understand. It simply behaves constantly across distances so large that the idea of far stops being useful, and across time so long that the word old becomes almost meaningless. If the universe communicates at all, it does so through messengers, not storytellers, not witnesses, but physical messengers. Light, particles, waves, and subtle patterns that drift through space carrying traces of where they came from. To understand the universe is to learn how to read these traces without ever touching their source. This is one of the quietest mysteries of all. How can we know anything about the most distant objects in existence when we can never travel to them, never sample them directly, never bring a piece of them home? And yet, we do know things. We know the temperatures of stars. We know the compositions of nebulae. We know that galaxies rotate, collide, and form clusters. We know that the universe expands and that the expansion accelerates. We know that black holes merge and ripple space-time. Most of this knowledge arrives through one messenger: light. Light is the universe's oldest reporter. It travels vast distances without needing a road. It crosses emptiness. It slips through gas. It bends around mass. It can be captured, split, analyzed, and transformed into information. When astronomers look at the sky, they are not merely seeing brightness. They are seeing encoded clues. Light carries frequency, and frequency carries meaning. A star does not simply glow. Its light contains signatures of the elements within it. Certain wavelengths are absorbed or emitted depending on atomic structure. The pattern becomes a fingerprint. This is how astronomers learn what stars are made of without ever touching them. They take the light, spread it into a spectrum, and read the missing and bright lines like a quiet language. Hydrogen leaves one set of lines, helium another. Carbon, oxygen, iron, sodium, and countless others leave their own. The universe writes its chemistry into light, but the story becomes more complex when motion is involved. If a galaxy moves away from us, its light stretches to longer wavelengths. This shift is called redshift. If it moves toward us, its light compresses to shorter wavelengths. This is how expansion reveals itself. Galaxies are not merely distant. They are drifting away, and the amount of drift correlates with distance. The farther the galaxy, the more its light is stretched. The universe's growth is written into the color of arriving photons. This sounds simple, and on paper it can be, but the real universe is noisy. Dust dims light, gas absorbs it, local motions complicate the pattern, instrumentation adds errors. Data must be corrected, refined, and checked again. Astronomy is not just awe. It is careful work performed at the edge of detectability. And still, light is only one messenger. There are others, and they reveal different layers of the universe. Consider neutrinos. Neutrinos are nearly massless particles produced in nuclear reactions, including those inside stars and in violent cosmic events. They pass through matter with almost no interaction. A neutrino can travel through an entire planet as if it were a faint mist. This makes neutrinos difficult to detect, but it also makes them powerful messengers. They can escape regions where light cannot. In some environments, light is trapped by dense matter. In the core of a collapsing star, photons scatter endlessly, unable to leave quickly. Neutrinos, however, can slip out, carrying information from deep within. To detect them, scientists build enormous detectors, often buried underground or submerged in water or ice, waiting for the rare moment a neutrino interacts with an atom and leaves a measurable trace. Neutrino astronomy is a newer sense, like hearing a faint tone after centuries of seeing only images. It offers a different kind of information, often tied to the most extreme events. Then, there are cosmic rays. These are high-energy particles, mostly protons and atomic nuclei, accelerated to extraordinary speeds by astrophysical processes. Some originate in the sun. Others come from supernova remnants, active galaxies, or unknown sources. Cosmic rays strike Earth's atmosphere and produce showers of secondary particles. They are evidence that the universe is not quiet even when it looks calm. Somewhere, in some distant region, energy is being concentrated and hurled into space. But cosmic rays are also frustrating. Their paths are bent by magnetic fields, so they rarely point directly back to their source. They are messages without a return address. They tell us that acceleration happens, but not always where. And then there are gravitational waves. These are not particles and not light. They are ripples in space-time itself, produced when massive objects accelerate violently, such as when black holes merge or neutron stars collide. Gravitational waves carry information that light cannot. They pass through matter almost unhindered, and they reveal motion on cosmic scales with a kind of purity. When a gravitational wave arrives at Earth, it slightly stretches and compresses space, a tiny change that requires exquisitely sensitive instruments to measure. The detection of these waves added a new channel of cosmic communication. For centuries, the universe was studied mainly through electromagnetic radiation. Visible light, radio, infrared, ultraviolet, X-rays, and gamma rays. Now, it is studied through space-time vibrations as well. This matters because different messengers reveal different truths. Light can be blocked. Gravitational waves cannot, at least not in the same way. Neutrinos can escape dense cores. Cosmic rays reveal energetic accelerators. Together, these channels form a more complete portrait of the universe. The mystery is not just what the universe is, but how we know what we know. We are cosmic detectives. We reconstruct events from traces. We infer causes from effects. we build models that must explain not one observation, but many simultaneously. The universe is the scene. The signals are the evidence. Theories are the reconstructions. And uncertainty is always present, not as a flaw, but as a measure of honesty. Some mysteries persist because the evidence is incomplete. Others persist because the evidence is contradictory. And some persist because the evidence is fundamentally limited by distance, time, or physics itself. This is where the universe becomes not only a physical story, but an epistemic one. What can be known? What can be measured? What can be tested? The boundaries of knowledge are themselves part of the universe's structure. Even within what can be measured, interpretation can be subtle. Take the question of the universe's expansion rate. Different measurement methods have produced values that do not perfectly agree. Some methods use nearby distance markers, others rely on early universe signals. The discrepancy is small in absolute terms, but significant for cosmology. If the difference remains after errors are ruled out, it could indicate new physics, or it could reveal hidden biases in data. This is how science advances, not by forcing agreement, but by studying disagreement carefully. The universe does not always cooperate with our desire for clarity. Sometimes it offers competing clues. And then there is the question of origin stories. Science can trace cosmic history back to a certain point with increasing confidence. But near the beginning, uncertainty grows. Processes become extreme. Theories collide. In that region, it is tempting to fill gaps with imagination, but the discipline of science is restraint. It says, we know this because it is supported. We suspect this because it fits but is not proven. We do not claim this because it cannot be tested. This restraint is not weakness, it is strength. It keeps the boundary between knowledge and speculation clean. In a universe where the unknown is vast, clarity about what is known matters. The universe also hides its secrets in plain sight. Many cosmic phenomena are visible, yet their mechanisms remain unclear. For example, galaxies form stars at rates that vary dramatically. Some galaxies burn brightly with star formation. Others are quiet and old. Why some systems ignite while others fade depends on gas supply, feedback from supernovae, black hole activity, environment, and history. Each factor is understood partially. Together, they form a complicated story, still being untangled. Or consider the behavior of magnetic fields in space. Magnetic fields thread through galaxies and clusters, shaping cosmic rays and gas dynamics. They influence star formation and the behavior of plasma. Yet the origin and evolution of cosmic magnetism remain active research areas. These are mysteries not because we cannot see the effects, but because the cause and effect chain is complex. The universe is not always a single variable system. It is interlocked. And then there are the mysteries that sit at the foundations. What is space, really? Is it continuous or granular? Is it a thing or a relationship between things? Does it have properties that change? When space expands, what is actually expanding? When gravity curves space-time, what exactly is curving? These questions are difficult because they interrogate the stage itself rather than the actors on it. Time is similar. We experience it as flow, but physics describes it as dimension. Yet the subjective feel of time, the arrow of time, the link between entropy and memory, and the apparent uniqueness of the present moment remain puzzling. The universe contains time, and we are time-bound observers inside it. That alone makes time hard to analyze from the outside, because there is no outside. In the midst of these mysteries, it is easy to think that the universe is unknowable, but that is not the lesson. The lesson is that knowledge comes in layers. Some layers are solid and stable. The existence of galaxies, the reality of expansion, the behavior of gravity in many regimes, the nuclear processes that power stars. Other layers remain fluid, the nature of dark matter, the identity of dark energy, the unification of quantum mechanics and gravity. And beyond these lie the unreachable, regions beyond the cosmic horizon. Information hidden behind event horizons, aspects of the early universe that may never be fully reconstructed. To live with these layers is to accept that the universe can be both understandable and mysterious at the same time. This is not contradiction. It is maturity. It means we can appreciate the progress of science without pretending it is finished. We can rest inside what is known without demanding that everything be explained tonight. There is a calming honesty in that. The universe becomes less like a locked door and more like a landscape. You can walk far into it, learn its terrain, map its structures, and still see mountains beyond. Mystery, in this view, is not a failure. It is the horizon line that keeps curiosity alive. And perhaps that is why the night sky continues to soothe. When you look up, you are not only looking at light, you are looking at information arriving late, stretched by expansion, altered by gravity, shaped by distance, and filtered by the limits of your instruments. You are looking at the universe's ability to send messages across vast emptiness. Each photon that reaches you has survived a journey that began long before you existed. It has crossed regions of space that contain almost nothing. It has slipped past dust, gas, and gravity, sometimes bent and delayed, sometimes stretched until it becomes invisible. The fact that any message arrives at all is astonishing. The universe is not only vast, it is legible, at least in part. And that partial legibility is enough to build a story of structure and expansion, of unseen matter and invisible energy, of collapsed stars and warped space-time, of beginnings traced through faint background light, of possible life on distant worlds, of a future shaped by forces we do not yet fully understand. And behind that story, always the quiet question, what else is out there? What else is possible? What else do the signals carry that we have not learned to read yet? As science improves, the universe will not become less mysterious, it will become more detailed, and therefore more intricate. We will see more, we will measure more, and we will realize how much more remains. That realization does not need to be alarming. It can be calming, because it means the universe is not small enough to be exhausted. It is not simple enough to be fully domesticated by human understanding. It remains wild in the best sense, vast, structured, indifferent, and yet full of patterns that can be learned. Tonight, you do not need to solve it. You do not need to answer its deepest questions. You only need to rest in the presence of something larger than your worries, something older than your stress, something patient enough to unfold across billions of years. The universe will still be there when you wake. Its signals will keep arriving. Its mysteries will remain. And its quiet, distant light will continue crossing the dark, carrying the story forward.